There we go. Happy Friday.
Happy Friday.
All right. I think we left off last time on CPUs.
Correct.
And specifically, we had just briefly covered that there's some internal cores to the CPU. There's really rapid storage, like L1, L2 cache that's really small. At the base layer of a CPU, there's an on-off switch, like a light switch transistor. And then there's a clock cycle that runs in the CPU as a whole. And each of these cores kind of follow that clock cycle as well. And then we talked about briefly how CPUs have there's an x86 variant and there's an ARM variant, and the difference is MIMO or SISO, which is multi-input, multi-output, or single input, single output. And what we were about to talk about was threading and parallel processing. Single output and multi-output matter in the context of parallel processing. So let's dive into it a little bit. I guess first off, Justin, you watched last week's. Did you have any questions?
I guess I had one read back that I wrote down,
Sure.
and that was on the BIOS, which I said the BIOS is the middleman software to start the signal clock cycle between the CPU and RAM. If I were to give one sentence to it, does that track?
Yeah. And just to crispen it, it's just a piece of software that sits on the motherboard that is not stored in the hard drive.
Got it.
And it's very lightweight. Every motherboard has it. And it allows you, it's kind of like the meta software that boots the actual operating system. So I could have multiple drives here, multiple operating systems, and the BIOS can choose which one to boot. But it comes with a bunch of other fancy features that really relate to the motherboard itself. So you can turn off cameras, you can increase clock cycles of RAM, you can do all kinds of overclocking and fancy stuff with it. But it's primarily used for selecting the hard drive.
Got it.
And then maybe turning on and off hardware encryption. One thing I didn't tell you about hardware encryption was some devices, not all of them, come with what's called a TPM. I can't remember the name of it, but it's actually just a little chip. There we go. It's actually just hold on. There we go. It's actually just a little chip that's really small. It's smaller than M2 drive. That just connects into the motherboard, and it's got a hardware serial level number on it, and so that sends a signal through there. It reads the serial and it can decrypt the device. A lot of modern computers have it. If you do a self build, it may not have it. You may have to buy it separately, but the BIOS can interact with that as well.
Got it.
Cool. All right, so we're starting to get a little bit more software centric here. So we need to talk about threads. A thread is basically the smallest sequence of programmed instructions that can be managed independently by a CPU scheduler. And we haven't talked about a CPU scheduler, but the CPU scheduler is basically a piece of software that's running through the CPU that schedules. I should talk about multi-threading first before I describe that. Let's talk about multi-threading. So think of this as a single instruction, single calculation running through the CPU. Multi-threading and parallel processing are two ways to send instructions through a computer. Multi-threading itself is the ability to have one set of instructions running in the computer, then pause that set of instructions, then start another set of instructions. Now that happens on what's called a process. So this whole thing would happen on what's called a process. And a process would happen on a core. So there's usually only one process per core, but there can be multiple threads running at one time. And the way that the threads run is they're just just cycling. You might have a computer program that's running, but then you have an interrupt and you need to pause that program and do something else. Well, now it's multi-threading because it did a calculation, paused it, started doing another calculation, finished that one, then came back to this calculation. That will have more relevance when we start to talk about threading in computer in like programming languages. But the bottom line is sometimes it's useful to pause one calculation, then do another one because it relies on the other calculation. It's happening in a different thread. So that's multi-threading, but it's all within one process. Parallel processing is a little different. It's actually multiple processes running. And the only way you can do parallel processing is with multiple cores. So if you had a CPU that only had one core, you couldn't do parallel processing on it. You would need a second CPU. Or in modern CPUs, usually you have 4 to 12 cores, sometimes up to 16. And that allows you to do, if you have 4 cores, 4 parallel processes at one time. And each of those parallel processes, each of those 4 could have multiple threads. And so there's no limit on the number of threads you can have, but the more threads you have, the slower your overall program is going to run. So, there's a useful limit. But if I wanted to train AI, for instance, you might hear that they like to do that on parallel processing. And the reason is that I want to run multiple sequences at the same time so that it halves the amount of time I have to train. And there's all kinds of fancy techniques to do that, but that's the difference between multi-threading and parallel processing. So back to these CPUs over here, ARM and x86, MIMO and SISO. Parallel processing can only happen on a MIMO CPU if it's only on one CPU, because you have multiple inputs and multiple outputs, and those inputs go into multiple cores, essentially. ARM is just one core. And so if I send in a signal, I can't send in multiple signals at one time to do multiple calculations. I could do multi-threading on ARM. I just can't do parallel processing. I would have to have multiple ARM CPUs. And I'd probably have to have some special orchestration software too if I was doing that. Does that make sense?
Mm-hmm.
Any questions there? Okay. So when I mentioned the scheduler before, a CPU scheduler will literally sit in here and it will schedule the threading based on priority. So what do I mean? Like antivirus a lot of times has higher priority than a lot of other applications on the computer. So you might be, typing in some website or something, Google Chrome's running, it's running on one thread, but your antivirus, periodically checks in on, whatever you're typing to make sure that you're safe or nothing's like injecting your computer, and it will pause the thread of Google Chrome, go to the antivirus thread will run, and then it'll go back to the thread of Google Chrome. So that's like an example, and it comes with priorities. So each thread has a priority, and the CPU schedule basically orders the priority of thread and calculations, and then it kind of like, it'll run call it a P1 thread, and then pause, and then it'll run a P0 thread because that just popped up. And then it'll finish that and go back to the P1 thread. And then maybe there's a P2 thread. So the P1 thread continues all the way until the P2, until it's done. And then the P2 takes over. So it's got a whole fancy priority system, but it's all based on this kind of start-stop mechanisms with multiple cores. Does that make sense?
Yeah, that makes sense to me.
Cool. If you ask me much more details about that, I'd probably have to go get my grad school work, or I won't remember exactly how they work, but there's algorithms for it. Okay. I don't think I'd talk about it anywhere else. So before I get into this, I want to quickly mention the difference between deterministic and non-deterministic. And then non-determ. Just put nistic on the end of that. So you probably hear the terms non-deterministic and deterministic a lot. Those have a super specific meaning in computer science that is different from the way that they're typically used. Deterministic means that I can run a set of instructions. Basically, a function takes an input and puts an output. That's a set of instructions. And and it will be the exact same every time. It will never vary in the output if I have the same input. Non-deterministic is different. Non-deterministic is if I put an input into a function, the output could be something totally different on multiple runs. That is different than stochastic. This is an important point. And we'll talk about this in a second until it kind of makes sense. So this is like same input, same output. Not that syso, but like just make the S same. Same input, same output. This is unknown. If I have a function that's like, y equals a times x, or f of x. Wow, I'm like failing here. Hold on. If a equals f of x, then this is an example of a deterministic function is, f of x is a plus b in our standard, math axioms for standard math. So a plus b equals, c or whatever. And so if I have 1 and 1, it's always going to equal 2 in the set of all real numbers. This gets into some stuff that I'm just being kind of vague with. I can talk to you guys about it later, but it's really deep in the weeds of computer science. The point is that a CPU should be deterministic, is deterministic, because if I send the same thread through those switches, I will always get the same output, assuming like the switches are set the same at the beginning. Non-deterministic is not really something you see in nature. Outside of maybe quantum mechanics right now. And that would be for any x that I put into the function, I might get a totally different a at a different time. And it's not a probability. I don't know what the outcome will be. It's completely non-deterministic. Stochastic is probability, right? So like the difference here would be if I put in x to a function, I now have a probability of a distribution over A. That is still deterministic. It's just stochastic. Meaning like there is a determined factor of what you will get and it falls on this distribution. It's not non-deterministic, which is totally unknown. But it is stochastic, so it's deterministic stochastic. Does that make sense? The reason I bring that up is that computers are deterministic, and occasionally they can be stochastic. They're never non-deterministic. Quantum computing may break that, but like regular computers. Okay. And you can go deep in the weeds on this. Kind of as deep as you want down the rabbit hole. And part of the reason I say this on this probability distribution is that inside of a function here, if something is stochastic, there's actually a random seed. You've seen a random seed in software. It's like a random number generator that is affecting the distribution. And that random number generator is a math equation that is deterministic. So it might be based on the clock speed of the computer, and at whatever the time is in the clock speed or in the clock of the computer, it uses that as the random number. But it's still deterministic because you can still get the same result if you have the same random seed. Does that make sense? Okay, sweet.
Yeah.
All right, moving on. I just wanted to make that point. Okay, human readable versus machine code. So source code, the word source code always means something that humans can read. It's in a language that's easy for us to understand. So a standard function that you may have seen, and what are your guys' degrees in? Anyone taken MATLAB class or ever touched Python?
Yeah.
Yeah. So you've seen an if statement before, where it's like if A is greater than B, return A. That is called source code. That's human readable to me, but a computer can't read that. Like those characters don't mean anything to a computer. So what you have to do is you have to get that that human readable code into computer code, computer readable code that we call machine code or binary code, the ones and zeros essentially. So the question is, how do I get my computer, my CPU, to be able to read this? And that happens through one of three methods, but I'll make it generic for a second. It's a translation step that turns the human readable code into binary code. And there's separate computer programs that do that. And they fall into one of three. One is called a compiler, one is called an interpreter, and one is called a just-in-time compiler. There are those three categories. They're right here. And so in order to run a program, not only do you need to write the source code, you need to have a compiler, an interpreter, or a just-in-time compiler on your computer that can then interpret it, feed it to the CPU, and let the CPU run the calculation, and then send you a result. Or make something happen. Okay, so what are each of those things in a little bit more detail? Because there are differences between them. Let's talk about, I'm going to zoom in here. Let's do this. Differences between them. So compilation turns a sequence of code into machine code before it runs on the CPU. Fully turned into machine code before you ever click the run button. Interpreting turns source code into machine code at runtime while the program is running. So each line by line, as I guess I should explain this, in a source code file, code always runs top to bottom, line by line. Now you can add functions and classes, and it ends up going like line, then into a function, then into a class, then into a function, but it's always top to bottom. Interpreters literally take the source code line by line, and as it's executing, it translates it into machine code, runs that line, puts an output, translates the next line, and just keeps going like that. That's an interpreted language. So compiled language takes that whole file, compiles it entirely, and gives you a piece of binary that you can then click run, and then it runs on the CPU. Interpreting is literally just like line by line by line. There's no compilation step. It's literally like interpreting as you go. Just-in-time compiler is kind of in the middle. And it basically compiles partially or has partially compiled components ahead of time that you're using, but also interprets it. So we'll talk about why that's important, why those options are important in a second, but those are the three types. Any questions on the three types before I get into kind of the more why?
No.
Cool. So common languages that are compiled, interpreted, and just-in-time compiled. Compiled languages, C++, C, Java, C#, Rust, and there's a bunch more. There's tons of languages these days. And each of those languages have compilers. They could have many compilers, but you only need one to run the program. Now, some compilers are more efficient in the way they translate things to machine code. But like, you know, C++ has GCC and it has Clang, and people have wars about which one you should use. And it also has Visual Studio if you're on Windows, that has a compiler with it. But the point is that a lot of those type of languages, those more rigorous, harder languages, are compiled. And we'll talk about a little bit, but they're faster. Interpreted languages like Python, JavaScript, TypeScript, PHP, Ruby, web scripting languages, a lot of scripting languages that are simpler are interpreted. So there's no headache of having to have a compiler, but you do have to have an interpreter. The interpreter could be the Python interpreter through the command line when you download python.exe. It could be your web browser that has compiled code that's an interpreter that will interpret your scripts and your web pages. And then there's just-in-time compiling. Java Eclipse framework has a just-in-time compiler. C#.NET framework has a just-in-time compiler, depending on what you're using. that are kind of in the middle of those two. Any questions on languages? Cool. Compilers, interpreters, and just-in-time compilers. What was I trying to say there? So here's an example of the compilers themselves. So in C++, in C#, you've got GCC, you've got Clang, you've got Visual Studio Compiler. In Java, it's the Java SDK. Probably heard Software Development Kit or Java Runtime Environment. Those are two separate things, but the SDK kit has the runtime environment in it, which lets you run applications. C#'s .NET framework, supported by Microsoft, has a compiler with it. For Python, there's a Python interpreter. For JavaScript, TypeScript, PHP, Ruby, and Ruby, it's all web browsers. With the exception of like React frameworks, which actually have like separate compilers with them that like compile it ahead of time. There's some nuance there in all of these. Like you can actually compile Python, but like you have to get a Python compiler. But for the most part, this is the general rules of the road. And then Java has Eclipse, and C# has the .NET framework. For runtime speed, the differences between the two. Compiling is by far the fastest. If it's compiled, you don't have to interpret it at each step. So it's pre-compiled. You've done all that work up front. You've capitalized on all your efficiencies, and now it can run very fast. So that's why C++ is significantly faster than Python. The slowest is interpreted because you have to go line by line by line. And then the middle of the road is just-in-time compiled. So just-in-time compiled is useful because you might be working on some sort of application in like the Eclipse framework that has like a little bit of UI components, and you're trying to build, some user functionality and all this stuff, and you want to test it. Well, if you have a lot of code, you don't want to wait 30 minutes for the code to compile. You have to like rebuild it entirely. It could take that long. It could take an hour. It could take 5 minutes. Depends on how big the application is. So instead, you click this button that says like, it's not just-in-time compiler, it just says run, but in that framework, but it uses pre-compiled components for a lot of the UI, and then it will interpret the other pieces as it goes along. Now, that's not what you would do if you were going to deliver it to a customer. You would compile the delivery of the build. But if you're a developer sitting here, having something take like 2 minutes to whip up versus like 30 minutes to compile is a big deal. And so that's kind of the differences between the two, or between the three. Difficulty to write. Usually compiled languages are way harder. And for reasons that we'll get into in a bit, but they have static types and a lot more rigorous things that you have to account for. The easiest is interpreted languages, and they're significantly easier. And then second hardest would be just-in-time. That's not really that accurate, to be honest. Like I would say just-in-time compiled languages are almost as hard, just as hard as, because some of them are the same as like the hardest difficulty. Speed of turning source code into machine code. So compiled is the slowest. When it does everything beforehand, but it takes a while because it's trying to make it like as efficient as it can in the compiler, depending on what settings you make. Interpreter is like way faster. It's like you run a Python script and it just runs like kind of immediately because it's doing line by line by line from turning the source code into machine code, not necessarily executing the program or a computation. And then just-in-time compilist is like in the middle of those two. Any questions on that stuff? Cool.
Actually, yeah, one quick question. So I remember, I think this was more when I started, but I remember hearing that, NCA does a lot more C++ and ACA was a lot more based in Python.
Yeah.
I guess in your opinion, how to the different languages or the different translators affect like autonomy development?
So there are reasons far beyond compilers and interpreters as to why those languages were chosen for those groups.
Mhm.
that we can get into in a little bit when I get down further. But
Okay.
from this specific perspective, NCA tried Python out and had built a Python system before I think you even got here, Justin.
Mhm.
And they ran into, because of this issue, the speed at runtime, they
Yeah.
ran into bottlenecks where they could not execute fast enough. So they switched to C++ so that the code would execute faster at runtime.
Sure.
Now, there are things you can do to make Python a little bit more efficient. Like there's some packages and stuff, but if you ask my opinion, Python should not be on an airplane.
Mhm.
And a lot of people around here know I'm pretty dogmatic about it. Kevin's pretty dogmatic about it. In R&D, it's okay. In actual production, it's a no-go.
Sure.
And almost nothing in actual production has Python unless it's like a completely separate computer with a UI or something. Because you need really deterministic. And when I say deterministic, I really mean like speed deterministic. Like you need to have a solid understanding of how fast your program's going to run, and
Yeah.
you're not going to run into a bottleneck. Now, there's actually a deeper thing here that we could get at on why like C++ and Python are bad, but like or Python's like bad for airplanes in production for like flight control, and why it's never used is and why almost nothing but C and C++ are used is actually memory management of resources within the computer. There are no guarantees that you won't run out of memory with Java, with Python, for example, because it does this thing called garbage collection in the background where once it runs out of resources, it tries to free up the resources and go back. We can get into that later. C++, you specify it all up front. So there's no issues. You're never going to run into that in C++ if you build your program correctly.
Got it. Okay. Thanks.
Yep. No worries. So we got 3 minutes left. What I'll do is just introduce this, and then we'll go over it in more depth next time. But it's funny, 4 years ago, when my wife first got into software, I think it was 5 years ago now, I wrote this out for her, this diagram. It was kind of like, this is the roadmap to, my view of jobs in computer science. And like, you can kind of like almost pick early now which ones you kind of want to focus on. Now she's a web developer, so she's like up in this world. But like this gives you an idea of like how to decompose to some degree the world of computing and computer languages. So you got your web development frameworks and the whole internet ecosystem. You've got desktop applications like, your regular words and stuff like that. You've got networking, which is like, you can lump in IT and cybersecurity and a bunch of stuff to there, but really how does data get from one point to another over like Ethernets and other ports? And then you've got robotics, which is like, how do trains work? How do cars work? How do robots work? How do actuators work on like, how does the SpaceX get something into space? Like that's kind of like that domain. I would say this is a bit of an oversimplification, but web development's maybe the easiest. Maybe tied with data science for the easiest. Networking's probably the second hardest. It's almost not even like a real thing, that not in the same lane as the others. And then robotics and embedded systems are way harder. And in fact, general purpose robotics is a lot easier than embedded systems. Embedded systems gets very hard and very niche very quick. So we'll talk about all this and kind of what frameworks and languages and stuff are fit into each domain. And then we'll kind of go through a little bit more in depth as to what these are. And Justin, hopefully this will be helpful to you, but we'll get to IP packets and TCP, UDP, broadcast, and how all that stuff works in future sessions. All righty.
Yeah, definitely. Looking forward to it.
Awesome. I'm going to stop the recording now.